Welcome to our town hall for the Apache Cassandra community. We've got Liran of monday.com, who is going to be talking about how they crafted a database from scratch using Cassandra, why they chose it, the benefits they saw, and so forth. So Liran, turning it over to you.
Hi, everyone. My name is Liran. I work for monday.com, and I'm very happy to be here. I've been invited to discuss the by far most challenging and impactful and interesting project I've worked on, which is mondayDB, a project that really shifted the entire data paradigm of the company, and had a major effect on the users and the future of the company. So let's start by understanding what is monday.com for those unfamiliar. In a sentence, monday.com is a platform. We call ourselves a work operation system, where you can really create a tailored tool to manage all the aspects of your work. You can manage all the processes of your work. You can collaborate on top of your data, automate your silos, and integrate with different systems you work on. And you do that without any requirement to code. So it's, in a way, you are programming a product for your company without programming. And let's see how it looks like. So the most basic entity is the table, which we call a board. And basically, a board is a very, very fancy table when you have a rich UI that you can define no matter what you want to manage. In this case, it's like a Scrum iteration for software development, but it can really be anything. We call each row in that table an item in Monday terminology. And we have about 50 kinds of such columns. Each column is shifted with its own UI, settings, abilities. On top of that board, you can filter by anything, sort by anything, aggregate by anything, group by anything. And each one of those columns has potential unique logic, how it behaves, how you filter, what the abilities you can filter on, aggregate on, etc. So it's very, very flexible in the kind of combinations you can tailor on top of that table. And then we can also have joins. So in this case, we can have another board, which is an higher view of the previous board, when you can see aggregation to sum up all the story points of all the items of each iteration. So it's both aggregation on top of join from another board. And you have the regular capabilities of spreadsheets, user-defined function, formula that you can really define any custom logic to be presented, and then also show that. And after you have this board, you can on top of that tailor dashboards and integration and apps and automations and docs, and you have API. So you can really tailor a product. And actually, we don't even have a single industry that is more than 1% of our clients. So it varies from software development to CRM and real estate management, and even churches. Nice anecdote is that many of the refugees camps in Ukraine were managed on top of monday.com. So it just gives you a glimpse of how flexible the system is. So it's very, very interesting, but also very challenging, because basically we really want it all. We are really greedy in our requirements. Usually when you are starting to design your system, so you gather the list of requirements, and then you are picking the most appropriate database for the job, right? Depending whether your data is mutable, it should be more time series or not, depending on the scale, depending on the pattern of writes or reads. But in our case, we are not a product. We are the platform where you build products on top of. So what do we choose? Let's go over to name a few of the requirements we need to satisfy. So first of all, the tables are schemaless, right? Each table is unique. It's a different structure. And by the way, that structure is dynamic, right? It's changing runtime all the time. We want to allow to filter and sort by anything without knowing in advance what the user is going to filter by. Data is mutable. We have thousands and sometimes hundreds of thousands of changes every second for the data. And also it needs to be reflected. So if two users are opening the same view, it's changes reflected immediately between the screens. We want isomorphic logics. So for example, in the mobile, we want to allow offline experience, or if the board is small enough, we don't want the round way from the back and forth. We can run it only on the client. We have user-defined functions, joins, aggregations. Table can be of any size. It needs to be fast enough to serve application. Limitless amount of tables. And because we have APIs, so we have really unpredictable load. Sometimes we have scripts or scripts that really loads that suddenly at a big burst of spikes. And of course, because we are at the heart of many companies, to the degree that when monday.com is down, the companies relying on us are down. We must be highly scalable, reliable, durable, fault tolerant, all the fancy words. So please raise your hand if you've ever had to pick a database that satisfies all those conditions. Like I know for sure that I have never done that. Okay, so obviously no one wants to reinvent the wheel. And for a very long time, we inspected solutions ready on the shelf for many different vendors. But ultimately, we just couldn't find something that satisfies all our requirements, whether it's because data is mutable, the unlimited amount of tables, because we don't know in advance what the user is going to filter by, or because of the user-defined function. And also, we had the problem that many of our logic was actually business logic tailored to the column, so it's not even SQL-like. We'll get to this in a moment. So we try to reach to companies and search for what other companies did when they faced similar problems. And we actually found out that many of the companies are tailored something for their needs, something internal to satisfy their conditions. And we read all the white papers they wrote and we discussed with some. And basically, we decided to build our own platform, which is mondayDB. So with that in mind, let's see what we actually achieved. Okay, so let's take a step backward to the era before mondayDB. And basically, in that era, our backend was very simplistic. We actually had MySQL with many replicas to handle the scale. And we just wrote one huge table where each item in that table, each row, it's the Monday item, and a big blob of JSON with all the column values. And when the user queried that table, we just threw it away to the client, and now the client had all the data. He could do whatever he'd like with it, filter, sort, aggregate, join. And this is like amazing for front-end developers, right? Because you have all the data, everything at your end, and you can really write any custom logic to do all you please. And this was amazing for us to build an amazing product. And the client-side developers were very happy about that. But client-side is limited. And you can't scale to some degree when all the data is moved to the client. Like there is limitless amount. There is no limitless amount of processing power, especially for mobile, but also for browser and software machines. And then we decided, of course, the natural movement is to move the things to the backend. So with mondayDB, we are still writing to the MySQL. This is still the source of truth, but we are also writing a view layer to the mondayDB. And this mondayDB component is now responsible for performing the actual query, to filter, to sort, and at the end return the IDs for the items satisfy the condition, the query, and only return the current page to the client in pages, 100 rows or so. So now the client is very slim, and it doesn't really matter whether the board has 1,000 or 1 million items, because anyway, the client only gets 100 items or so at a time. So this was like the motivation. And let's understand the key concepts of our solution. So first of all, while in a regular traditional RDBMS database like MySQL, the row is king, and basically the basic atomic unit of data is the row stored in disk. In a columnar storage like ours, it's actually the column. So we store all the values of the column, for example, all the status values done, working on it, not started. We store them as a single unit together on disk. So if on the left you can see how the table looks like, usually in the columnar storage, you can imagine we have two different files, one file with all the values of the owner, and one file with all the values of the status. Now, why this works really well for mondayDB is because imagine you have a board of 20 columns, and most of our queries are not by many columns. Like you only filter by status, for example. So in order to understand what items satisfied the condition of, let's say, status equals done, we only need to fetch 5% of the data. We only need to fetch the status column involved in the query, and then we only need to fetch it and parse it and process just a fraction of the data. Secondly, most of the columns are actually very sparse. So a lot of time we don't even need to process a lot of data. In contrary, if it would have been a regular traditional table, we need to scan all the table or start introducing indexes, which in our case is very problematic because, again, the structure is very dynamic, it's constantly changing, and we don't even know in advance what the user gonna filter by. Moreover, one of the advantages of columnar format is that now we can have many optimizations and pre-calculations on top of each column. For example, we can have indexes. If it's a number, we can have the min max value. We can have Bloom filters, or if it's a low cardinality column like status, we can store in advance all the item IDs of each unique values. And then filtering by that value is practically no effort, and many more. So how do we even update a single cell when your format is columnar? So remember, we need to fetch the entire column data because this is the basic unit of data we have. This is the most granular level. So even if we are changing just single cell from stack to done, we still need to fetch the entire column. We need to locate that cell in the column data and then write the updated column data. And of course, this can happen in parallel by many users working on that column. So we need to lock. So this, of course, doesn't make sense, right? We have like the many thousands of changes of those little cell changes every second. We can't fetch the entire column and rewrite it each time. And this is where our Lambda architecture comes to rescue. So not to get confused with AWS Lambda functions, the Lambda architecture was invented by the big data industry, and the purpose was to allow them to have heavy computations on top of the data, but still, even though those calculations take time, still be able to serve recently changed data fresh in the queries. So how it works. We have the speed layer. This is where we holds and buffers all the recently changed data. In Monday example, these are all the cells changed over the last hour. We have the batch layer, which holds all the historical data. And when we feel we accumulated enough changes, or when an interval of 1 hour arrives, we just flush the data from the speed layer to the batch layer. And then when we have a query in runtime, we fetch from both speed layer and batch layer. We merge them and then serve the query by executing the logic. Now we are using Redis for the speed layer, and we are using Cassandra as the storage of the batch layer. Okay, so let's see how a flow looks like. Let's start with the write flow. So we said we have a cell. The user changed only a single cell from stack to done. We are just buffering it in the speed layer in Redis. Now this is O1 operation, it's very fast, and basically we are done. Now we keep accumulating more and more changes like that. And when we accumulated enough, we are taking the last snapshot of the data from the batch layer. We take all the things we accumulated during that last hour, we merge them, and then write back to the Cassandra, to the batch layer. And when we read, like I said earlier, we are just in the server layer, fetching from both layers, merging, and then executing the query. So what did we gain? First of all, we solved the problem of fetching and rewriting the entire column upon each single cell update. And also, it's very fast to make changes. Moreover, because the flash is happening in the background and no user is waiting for it, we can actually enable a lot of heavy pre-calculations on all the data. For example, we know that 99% of our queries are sorted by item ID, so we can already in advance sort the data by item ID. So 99% of the queries, we don't even need to run the sort logic. We can have compactions, we can have aggregations in advance. We can build Bloom filters of other structures. So it's very, very powerful that we can take the time to run those heavy pre-calculations. And of course, the data that was just ingested to the system is immediately available to the users. Another concept is that our storage is completely separated from the compute layer. So remember, the Cassandra is holding all the data of all the boards. And when we need more data, we can scale Cassandra up. We have a constant amount of server for Cassandra. However, our users are very dynamic, because on weekends we have low usage of the system. On US daytime, we have higher usage of the system. So we can just in Kubernetes add or reduce the amount of pods that process the data and actually run the queries according to the usage of the system. So it's also very elastic. Now, let's talk a bit about how we use Cassandra as our storage layer. So basically, the partition key is a combination of the board's column identifier, which is really the board ID and the column ID, and also a bucket ID. Now, why do we need the bucket ID? Because we want to follow the best practices of Cassandra to not have many big partitions, because most of our boards are relatively small, but most of our columns, so we are relatively small, but from time to time, you can have like really huge column with hundreds of megabytes or even gigas of megabytes. So what we do, we split the data to buckets. And because the bucket ID is part of the partition key, then the partition key can never be more than 1 megabyte, because this is how we split the data. So what we did, in bucket 0, we treat it specially. Sorry. In bucket 0, we store the bucket's metadata. And we only store it if we have more than a single bucket. So usually when the column is small, we don't have any bucket metadata. We only have bucket 0. And then the value is just the cell values of that column. All the statuses, like done, 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 stack, stack, stack. However, if the bucket is big, for example, 4 megabytes, sorry, we split the data for 4 different partitions records. So now in the first bucket of 0, we'll have a bucket metadata pointing us where is the rest located. In this case, in bucket 1, 2, and 3. So now each partition contains a quarter of the data. So basically the flow is very simplistic. We read bucket 0. If there isn't a bucket metadata, we know we have everything. But if there is bucket metadata, then now we fetch in parallel all the rest of the data. How do we update the data when we flush? Basically, we take a look at the bucket metadata. We see so far we are using 0, 1, 2, and 3. So we are writing the rest of the new data to bucket first 4, 5, and 6. And only after we are finished, we are overwriting bucket 0 with the new reference. So this is very cool because now, even though we have a data split into 4 different partitions, the readers are always seeing a consistent view of the data, because while we still didn't finish writing 4, 5, and 6, they will just have zero bucket with reference to the previous version of the data. And then we are finished, we are immediately, once we are overriding bucket 0, everyone reading from now on will see the new updated buckets. And then we can delete like the old buckets in the background. So what did we gain? Even though most of our tables are small, we didn't compromise them. For them, it's only a single operation to fetch all the data. Only for those bigger, it's like 2 operations in terms of time, because the first time to fetch the first bucket, and then in parallel fetch all the rest. Also, the update of the bucket is atomic. We didn't need to introduce locks or anything of this sort, and the client and the readers always see a consistent view of the data in the batch layer. And by the way, we have a patent on this technique. And why did we use Cassandra as the storage layer to begin with? So because of all the advantages that it's really battle-proven, highly available, highly resilient. The latency is very, very low. And we have like neat features like point-in-time backup recovery, which we already used one time in the past. And also it's a storage, so we can already take advantage of Cassandra for other metadata tables and things required for the operation. Now, we released the first iteration of mondayDB about half a year ago, and we already see like huge improvement, about 3 times faster for big boards. And even in this case, most of the time isn't even going for mondayDB, it's going for other aspects of the system like permissions and other things. And soon we'll also release a version that even improves this by 3 factors more. Let's see how it looks like before mondayDB and with mondayDB. So to the left, you can see a very big board of ours loaded with mondayDB, and to the right when mondayDB is disabled. So you can see that mondayDB board is loaded, and to the right, like how it's used to get loaded before, like for a very linked board with a lot of joins, it was just very, very slow. Thank you very much. I hope you enjoyed our use case.
Thanks, everybody. Have a good one. Hope to see you soon. Bye-bye.